Okay. So in the previous lecture we have seen how the lossless line will be. Okay, the lossless line will be having the propagation constant purely imaginary. So only gamma is equals to j beta only. Okay, so alpha will be equals to 0. So if you take the lossless line, now if you want to find the input impedance of that lossless line, okay, now how will be the input impedance for short circuit and open circuit lines? Already you know the input impedance. The impedance is dependent on the length of the line, right? The input impedance or impedance is dependent on the length of the line. So that's why. Already you know this is a function of beta L, means it is a function of length of the line. Either it may be physical length or electrical length. So suppose if you take a lossless short circuit line. Suppose if you are making the ZL is equals to 0, means short circuit line. Now the input impedance of the short circuit line can be represented as ZSC. Okay, so ZSC. So ZSC is equals to JZ0 tan beta L. In the previous class we have seen, so ZSC is equals to JZ0 tan beta L, and ZOC is equals to minus Z0 JZ0 cot beta L. So these are the things you should remember. And now what happens? Already you know the impedance is dependent on the length of the line. Either it may be an electrical length or a physical length. Suppose if the physical length is varying in between 0 and lambda by 4, 0 and lambda by 4, now what happens? If I represent the length in the physical length, I have to multiply with beta to all this. If I multiply beta with this, it will be 0 only. It will be beta L. Beta means what? 2 pi by lambda. Then you will get pi by 2 here. Okay. So if I multiply with beta here, it will be 0. It will be beta L. It will be, if I multiply lambda by 4 with beta, means 2 pi by lambda, you will get pi by 2. So like that. Okay. Suppose if you are taking the length of the line in between 0 and lambda by 4 or in between 0 and pi by 2, now what will be the input impedance of the short circuit line? Will be inductive. Means suppose if you are taking the angle value, beta L value in between 0 and pi by 2, means the first quadrant. In the first quadrant the tan function will be positive. If it is positive, this tan beta L is positive, JZ0. So JZ0 is nothing but it is a purely inductive component, right? So that's why the input impedance of the short circuited line will be inductive in nature. The input impedance will be inductive in nature. So these statements are very helpful in solving the questions. Okay, so mostly they are very helpful in the engineering services examination and public sector examinations. Okay, so because the time will be given very less, so that's why you have to do the smart work. So that's why you should remember this kind of statements. Okay, so the input impedance of the short circuit line in between for the length between 0 to pi by 2 will be inductive nature. Okay, now if the same line in between pi by 2, suppose for the length if you are taking lambda by 4 to lambda by 2, okay, if the length of the line is in between lambda by 4 to lambda by 2, means pi by electrical length in between pi by 2 to pi, now the same line will be acting as a capacitive. The input impedance of the same line will be capacitive in nature, right? The nature of the impedance will be varying with respect to the length. Why? Suppose if you are taking the length in between pi by 2 to pi, what happens? If you are taking pi by 2 to pi, means it is in the second quadrant. Okay, so tan function is negative in the second quadrant, so the entire result will be negative. So minus JZ0 will be there. Minus JZ0 is the capacitive in nature. Okay, so that's why the input impedance of the short circuit line for the length between pi by 2 to pi will be, or lambda by 4 to lambda by 2 will be capacitive in nature. Okay, the input impedance will be capacitive in nature. So for this, the exact opposite to this, if you are finding the input impedance of the open circuit line, it will be exact to the short circuited, exact opposite to the short circuited line. If you observe this, it is ZOC. ZOC is equals to minus JZ0 cot beta L. Okay, so this is the input impedance of the short circuited line. Now, if you are taking the length in between 0 and lambda by 4 or 0 and pi by 2, okay, for the electrical length, now the ZOC is equals to, the ZOC means the input impedance of the open circuited line will be capacitive in nature, because in the first quadrant it will be cot is positive and minus into positive will be negative only. Okay, negative into positive is negative. So that's why it is capacitive in nature, right? So similarly, this will be the inductive in nature, right? So this is very, very important. Now if you come to the next concept, the reflection coefficient. Already you know how the reflection coefficient, how the reflection takes place. Suppose if the two mediums are different, suppose if the wave is going from one medium to another medium, if the two different mediums are present, then there will be a portion of energy will be reflected back. Okay, so this is called as the reflection. That means if there is a mismatch between the two mediums, okay, in which the wave is propagating, and there will be definitely a reflection of the wave. Okay, so that is called as the reflected wave. So already you know, in any medium or a line, we are talking about the transmission lines now. Okay, in any medium or a line. Okay, so on the line there will be two kinds of waves. One is forward wave and one is reflected wave. That means one is positive x directed wave, one is negative x directed wave. Okay, already we have we know V of x. V of x means the voltage at any x from the load, right? So this is the generalized expression, and in place of V naught, right? What is V naught? Here I am writing V naught means, so in the previous lecture we have seen V naught is equals to some VL into ZL plus Z0 divided by 2ZL, right? So it is like that. So I am replacing that VL into ZL plus Z0 divided by 2ZL as V naught. Okay, just I am simplifying like this. Okay, now V of x is equals to V naught into e power gamma x plus V naught into ZL minus Z0 divided by ZL plus Z0. Okay, ZL minus Z0 divided by ZL plus Z0 into e power minus gamma x. This is the V of x at any distance from the, it is the voltage at any distance from the load. Now already you know, this is what it is. It is negative x directed wave, it is a positive x directed wave. Negative x directed wave means what? From the negative x directed wave means what? From the source to load. Always observe. Okay, don't think that negative x directed wave is a reflected wave. Okay, because we are calculating the parameters, we are analyzing the line from the load point of view. So that's why always the x increasing direction will be what? The reflected wave. Means positive x directed wave will be the reflected wave and negative x directed will be the forward wave. Okay, so that's why this is a negative x directed wave. So this is called as the forward wave, and this is the positive x directed wave. So this is called as reflected wave. So this is a forward wave and reflected wave. And now already you know, if ZL is equals to Z0, now what happens? This reflected wave will be disappeared, right? Now if you are taking a lossless line, so what is meant by lossless line? Lossless line will be gamma is equals to J beta. If you are putting J beta here, we are getting V naught into e power J beta x plus ZL minus Z0 divided by ZL plus Z0 into e power J minus J beta x. Okay, so already you know what is the reflection coefficient. Reflection coefficient is the fraction of reflected component to the total incident component. Okay, what is the reflected component? This is VR divided by VF. So what is the reflected component in this? This entire is the reflected component. This entire is the reflected component. This is the forward component. Okay, this portion is the reflected component and this portion is the forward component, right? This is the reflected component, this is the forward component. So this one divided by this one will give you ZL minus Z0 divided by ZL plus Z0 into e power minus J2 beta x. So this is called as the reflection coefficient. Now it is a function of x, right? These all are constants. This is a function of x. So that's why it is represented as gamma of x. Okay. So what is the gamma of x? If you put x is equals to any value, it will give you the reflection coefficient at that instant. Okay. So it will give you the reflection coefficient at that instant. So this is called as the reflection coefficient at any distance. Okay. It is very, 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 very important. If you are aware of the reflection coefficient at any distance, and it will be very easy for you. Okay. The analysis of the transmission lines are very easy. Okay. You have to follow on systematic way. Okay. You have to follow one systematic way. So definitely the subject will be very easy. So suppose if you are putting x is equals to 0, already you know x is equals to 0 means what? It is called as the reflection coefficient at the load. So at x is equals to 0, gamma of 0 is equals to gamma at load, gamma load. And some people will represent only simply with gamma only. Gamma load can simply be represented with gamma only. So that's why gamma of 0 is equals to gamma load is equals to ZL minus Z0 divided by ZL plus Z0. So e power 0 will be 1. Okay, so that's why this is called as the reflection coefficient at the load. So this is equals to, see, observe this. Already you know it is a ZL minus Z0 divided by ZL plus Z0 is called as the gamma. So I am representing this one as mod gamma at an angle theta. Why mod gamma at an angle theta means, observe this. This is ZL and Z0. The ZL, suppose if you are taking a lossless line, the Z0 will be real value. Z0 will be real value. But ZL, it is not in my hands, right? So it may be positive, negative, means positive, negative means what? Positive reactance may be there and negative reactance may be there. That means capacitive may be there and inductive may be there, and short circuit may be there and open circuit may be there. Okay. So it generally it is a complex load. Generally it is a complex, or maybe it may be a complex load. Okay. So the load may be in general a complex. So that's why it will give the entire result will give you the complex value. So that's why mod gamma at an angle. So I have to represent this entire complex value as mod gamma at an angle theta. So this is the point. Okay. Suppose if it is a real value, now no need to write this mod gamma at an angle theta. Theta will be 0. Okay. Mod gamma is equals to gamma only. Okay. So this is the point you have to understand. Okay. So now what is the theta? Here theta represents the phase angle between VR and VF. So it is the phase angle between the reflected voltage to the forward voltage. Okay. So this is a very, very important point. So theta representing the reflection, it is the angle of the reflection coefficient. It is the angle of the reflection coefficient. What is mod gamma? It is the magnitude of the reflection coefficient. In general, the reflection coefficient is complex in nature, right? Complex in nature. Here we should give very importance. We should give very importance to the theta. You should give very importance to the theta. Suppose if you are going to the EM waves concept, here the theta is not that much effective. Okay, only gamma is we define. Only gamma we define. But here we are defining mod gamma. Mod gamma and gamma must not be confused. Mod gamma is magnitude only. It will not define the angle, right? So here the mod gamma and theta are very, very important. So that's why don't get confused with the mod gamma and gamma. Okay, gamma is the complete reflection coefficient. That means it includes with the theta. Okay, mod gamma is only the magnitude. Okay, very, very important. So generally the people will do the mistake here only. Okay, they consider mod gamma as gamma only. Okay, so if you are taking mod gamma means mod can take two values, positive and negative. That is the point you have to understand. Okay, suppose if you are taking the positive value, then the theta will be 0, right? If you are taking the negative value, then the theta will be 180 degrees. So that's why the theta differs. Okay, so this is the point. Now, so this is called as the gamma at load. That means reflection coefficient at the load. Now, if you are, see, observe this. I am defining the reflection coefficient at the load. Reflection coefficient at the load as load impedance minus characteristic impedance divided by load impedance plus characteristic impedance. What is the, see here, it is the reflection coefficient at the load. Now if I want to find the reflection coefficient at any distance, now what can I write? Reflection coefficient at any distance is equals to the impedance at any distance minus minus Z naught divided by impedance at any distance plus Z naught. This is the logic you have to understand. Okay. So if I want to define the reflection coefficient at any point, you have to first find the impedance at that point. If you know the impedance at that point, you can easily find the reflection coefficient. Okay. So that's why gamma of x is equals to Z of x minus Z naught divided by Z of x plus Z naught. Okay. So this is a very, very important point. Now, if you observe this, see, it is a mod gamma. This is mod gamma. So mod gamma value will be in between, the range of mod gamma will be in between 0 and 1. Okay. Suppose if you are writing ZL is equals to Z naught, then this will be 0. Okay. If there is a large mismatch between the ZL and Z naught, then ZL and Z naught will be 1. Okay. So this is a very, very important point you should understand. Okay. So this is the maximum value will be 1. So maximum value will be 1 means what? It is a complete mismatch. So this is called as the complete mismatched condition. Okay. So if you are taking the mod gamma is equals to 1 means it is called as complete mismatch. It is called as the complete matched condition. Okay, it is called as complete matched condition. So suppose if you are having gamma is equals to 0, mod gamma is equals to 0 means it is complete match. Okay, if you are taking gamma is equals to 1 means it is called as the complete mismatched condition. Okay, so the maximum value of mod gamma is 1. The maximum value of the mod gamma is 1. Now come to the next concept. So there are some cases are there when we are getting the mod gamma is 1. Okay, mod gamma is 1 means what? There is a complete mismatch condition. Okay, complete mismatched condition. Suppose what are the complete mismatched condition? Now come to these 4 cases. See, observe this. ZL is equals to J R naught. And Z naught is equals to R naught. What is ZL is equals to J R naught? ZL is equals to J R naught means it is an inductive load. It is an inductive load, right? Z naught is equals to R naught. Z naught is equals to R naught means it is a lossless line. It is a purely, so Z naught is equals to R naught means what? It is a real. Z naught is real. Characteristic impedance is real means it is purely lossless line. Right? Suppose if you are taking a line of lossless and you are terminating the line with the inductive load. Now what happens? Now gamma will be 1 at an angle 90. So how we are getting this? ZL minus Z naught divided by ZL plus Z naught. ZL minus Z naught divided by ZL plus Z naught. What will be this? ZL is how much? J R naught minus R naught divided by J R naught plus R naught. Okay, if you solve this, how much you will get? 1 at an angle 90. Okay, you will get mod gamma is equals to J. So that is the point you have to understand. Okay, so mod gamma is equals to J means what? J can be written as 1 at an angle 90 degrees. So this is the point you have to understand. Okay, so now what is the mod gamma? Mod gamma will be 1. What is the angle of gamma? Angle of gamma is equals to 90 degrees. Here mod gamma is 1, angle of gamma is 90. Okay, it is a very, very important. You have to remember this. You have to by heart this. Definitely. Okay, no need to by heart if you are having a concept. Okay, suppose ZL is equals to minus J R naught. Z naught is equals to R naught means it is a capacitive load and a lossless line. Capacitive load and a lossless line. Again, you will get how much you will get? 1 at an angle minus 90 degrees. So mod gamma is equals to how much? 1 and the angle of gamma is equals to 90 degrees. What is the angle of gamma? It is the angle of the reflection coefficient. What is the angle of reflection coefficient? It is the phase angle between the reflected voltage phasor to the forward voltage phasor. Now come to this one. ZL is equals to infinity. If ZL is equals to infinity means, if ZL is equals to infinity means it is an open circuited load. The line is open. Okay. If Z naught is equals to R naught, that is called as the, if you come to this condition, Z naught is equals to R naught. It is a lossless line and open circuited load. Okay. That lossless line is open circuited. If the lossless line is open circuited, now what will be the reflection reflection coefficient here. The reflection coefficient will be 1 at an angle 0. It is mod gamma is equals to 1. So for these all cases, what we are getting? Mod gamma is equals to 1 only. Now come to the next case. ZL is equals to 0 means it is a short circuited load. Right? It is a short circuited line. The load is short circuited and the line is lossless line. Okay, if the lossless line is short circuited, now what will be the reflection coefficient? 1 at an angle 180 degrees. So you will get what? Here, finally you will get here -1. Right? So that's why -1 can be written as 1 at an angle 180 degrees. So mod gamma is equals to 1 here. Suppose if you are observing these all 4 cases, so in all 4 cases 1 mod gamma is equals to 1 at different angles. Okay, different phase angles. Okay, so these are the very unique complete mismatch conditions, so you have to understand. Okay, so this is a very important thing, and they will be used for the analysis of the Smith chart also, and you have to remember that. So observe this in the given question. Suppose if the inductive load is given and the lossless line is given, so definitely you can easily find the, without solving you can find the answer, right? Mostly this kind of analysis will be useful for the public sector unit examination, right? Next, come to the position of voltage and voltage maximus and voltage minimus. So when you will get voltage maximus and voltage minimus means, already you know, when there is a reflection of the wave, so there will be two kind of waves will be appeared on the line, two kinds of waves will be appeared on the line, that is called as the forward wave and reflected wave, forward wave and reflected wave, and this formation of forward wave and reflected wave on the line is called as the standing wave, right? So why it is called a standing wave means, when there is a standing wave, what happens? Suppose if you observe this, suppose if you are observing this, it is a harmonic in nature, it is also harmonic in nature, it is having some, observe this, it is having some magnitude, but it is a harmonic in nature, right? It is also harmonic in nature, right or not? Now, why it is e power j theta term means harmonic, right? Harmonic, it is also harmonic. So that means it is a harmonic means it is a periodic in nature, right? So when the two periodic waves are traveling in a line and both are in opposite direction. So which kind of periodic waves are these? One is a forward wave, one is a reflected wave. So when that one is a forward wave is going on the line and one is a reflected wave is going on the line, okay, so there will be some cancellation will occur, some addition of the points will be occurred. So this is the point you have to understand. Okay, when two periodic waves are traveling in opposite directions on the same line, what happens? There exists voltage maximus and voltage minimus. This is the point you have to understand. So these two waves are traveling in opposite directions and they are periodic. So what happens? There exists periodic additions and cancellations on the line. That is the point you have to understand. Okay, there exist periodic additions and cancellations on the line. Okay, because they are the periodic. Okay, so periodic additions and periodic cancellations. So at wherever the periodic additions are taking place, then there exists a voltage maxima. Whenever the periodic cancellations are taking place, then there exists a voltage minima. Right or not? So whenever there exists a voltage maxima and voltage minima, so this kind of formation of voltage maximas or voltage minimas are called as the standing wave, right? So whenever you are having a standing wave, so you should find the positions of the standing wave, right? So where the positions of the standing wave means what? The positions of the voltage maximas or minimas. So where there exists a voltage maxima, where there exists a voltage minima. Similarly, where there exists a current maxima, where there exists current minima. So like that. Okay. Suppose if you are, so when there exists a voltage maxima, so voltage maxima, when the addition maxima means what? When you will get the maxima, whenever the phases of the forward wave and the reflected wave are equal, means they are in phase. Not equal actually, exactly. Okay, when the forward wave and reflected wave are in phase, then the voltage maximas will occur, because if they are in phase means the voltages will be, the voltage phasors will be added. The voltage phasors will be added. So that's why the voltage maximas will occur. Okay, when there exists a cancellation, cancellation means when the forward wave and reflected wave will be having a out of phase. out of phase point. So at the out of phase points, you will get cancellations. So there you will get the voltage minimas, right? So this is one phase and another phase. These are the two phases, right? This is the theta, this is the theta. Observe this. This is the phase difference is how much? It is the phase difference between how much? It is beta x minus of minus beta x. It is called as the 2 beta x. The phase difference is 2 beta x, right? If the 2 beta x is 2n pi, observe this. If the 2 beta x is 2n pi plus theta, observe this. Y means, why I am writing this theta? Why I am writing this theta means it is producing how much angle? It is beta x. It is minus beta x. Now what is the angle of this? The angle of this one is theta. So the angle of this entire component is how much? Minus beta x plus theta. Right? This is how much? Beta x. So beta x minus beta x plus theta. Okay? So that's why what is the phase difference between these two? So beta x minus beta x plus theta. It will give you 2 beta x plus theta. 2 beta x minus theta is equals to 2n pi. Because they are all in phase. Right? So that's why 2 beta x max is equals to theta. 2 beta x max is equals to 2n pi plus theta. So these are called as the positions of the voltage maximas. These are called as the positions of voltage maximas. What is n? N is equals to 1, 2, 3, 4, 5. Okay? N is equals to 0, 1, 2, 3, 4, 5. 0. It is starting from 0. This is the point. You have to remember this. It is n is equals to 0. So n is equals to 0 represents at first maxima. N is equals to 0 represent it is the first maxima. Right? N is equals to 1, second maxima. N is equals to 2, third maxima. N is equals to 4. N is equals to 3, fourth maxima. Like that. So n is equals to 0 represents the first maxima. Always remember. Mostly. Okay? So you have to observe that these are called as the positions of the voltage maximas. Okay? So whenever there is a position of voltage maxima and there exists current minimas. There exists current minima. Because Z max is equals to V max divided by I min. Okay? Z max is equals to V max divided by I min. So this is the point you have to understand. Suppose if you know this, and it can be very easy for you. So for current minimum, you will get maximum impedance. Okay, whenever there is a maximum impedance means there will be more voltage across that impedance. So this is the point. So whenever there exists a voltage maxima, there exists current minima and there exists impedance maxima. So that's why the voltage maximas are coinciding with the current minimas and the voltage maximas are coinciding with the impedance maximas. So wherever there exists a voltage maxima, there exists impedance maxima also and there exists current minima. So these are a very, very important point. Right? So these are called as the positions of the voltage maximas or positions of the current minimas are called as positions of the impedance maximas. Okay? You don't be confined only to the voltage maximas. Okay? You have to know something more. Now come to the positions of the voltage minima. Okay? So when you will get the positions of voltage minima. So whenever there is a cancellation. Okay? The periodic cancellation will exist, right? So that's why the phase difference between this one and this one will be 2n plus 1 into pi. They are called as the out of phase points. Okay? So if these two are out of phase, so 2 beta x min minus theta is equals to 2n plus 1 into pi means out of phase. Okay? Pi means out of phase. So if n is equals to 0, it will be pi, n is equals to 1, it will be 3 pi, 5 pi, 7 pi, 5 pi, 7 pi, like that. So they are out of phase points. So right? So these are called as the voltage minimas. Why first I am writing voltage minimas means I am taking the voltage phasor. So that's why first of all I am writing the voltage minimas. Right? Suppose if I write the current equation I of x, then I should write positions of the current maximas or current minimas. Okay? So now this is the 2 beta x min is equals to 2n plus 1 into pi plus theta. Okay, always remember what is theta. Theta represents the angle of the reflection coefficient. The angle of the ZL minus Z0 divided by ZL plus Z0. called as angle of the reflection coefficient. Okay. So here the positions of the voltage minimas. So positions of the voltage minimas are nothing but the current maximas. Okay. Voltage minima means what? Current will be maximum. Voltage minima means what will be the Z? Z also will be minimum. Z or impedance minimum. Okay. So voltage minimas are called as the impedance minimas, are also called as current maxima positions. Okay. So this is a very important point you should understand. Now, so you know n is equals to 0 represents what? First maxima or first minima. So that is the point. Now, so we came to know the positions of voltage maximas will occur, positions of current maximas will occur, right? Now what will be the difference between the two consecutive voltage maximas? What is the distance between two consecutive voltage maximas or two consecutive voltage minimas? Suppose if you are taking x max, suppose if you are putting n is equals to 1, if you put n is equals to 1, then you will get x max 1, right? Suppose if you put n is equals, let us suppose if you put n is equals to 0 here, how much you will get? 2 beta x max is equals to some theta, right? Now what will be the, suppose if you put n is equals to 1, now you will get 2 beta x max 2 is equals to 2 pi plus theta. If you subtract these two, x max, if you find x max 2 minus x max 1, 2 consecutive, by putting n is equals to 1 time, n is equals to 0 one time, n is equals to 1 time. Now if you find x max 2 minus x max 1, that means the distance between two consecutive x maxes. Okay. Then now what you will get? You will get lambda by 2, because if you write 2 beta as 2 pi by lambda, then you will get finally the distance between two maximas. Two maximas will be lambda by 2. Two maximas will be lambda by 2. And from this one only, what is the phase difference between this one and this one? What is the phase difference between this one and this one? Suppose if you put n is equals to 0, this will be theta only. Suppose if you put n is equals to 1, if you put n is equals to 1, what it is? It is 3 pi, right? N is equals to 1, it will be 3 pi, right? Suppose if you are taking, not this one, come to this one. Okay, if you are putting n is equals to 0, it will be how much? It will be theta only. 2 beta x max is equals to theta only. Suppose if you are putting n is equals to 1, it will be 2 pi plus theta. Suppose if you subtract these two, then what will be the phase? It will be 2 pi plus theta minus theta. The phase difference will be 2 pi. So for consecutive x max, so how much will be the phase difference? The phase difference will be 2 pi, right? The phase shift attained by the wave between two consecutive x maxes is equals to 2 pi. That means if the wave traveling at a distance of lambda by 2, how much phase shift will be attained? If the wave travels for a distance of lambda by 2, how much phase shift will be attained? The phase shift will be attained will be 2 pi. Okay. So this concept is also used in the Smith chart. Okay. Right or not? For lambda by 2 distance, how much phase shift will be occurring? The phase shift will be occurring 2 pi. It is a very important point. And one more important point is two consecutive x maximas. Two consecutive x maximas. The difference between two consecutive x maximas will be lambda by 2. Okay. Now, and after completion of this, the positions of voltage maximas and minimas are obtained. Okay. We came to know voltage maxima, we came to know voltage minima or current maxima or current minima, and from this we define the standing wave ratio. So what is the standing wave ratio? Vmax divided by Vmin. The voltage max divided by voltage min is called as the voltage standing wave ratio, VSWR. Suppose if I write current max divided by current minima, this is called as the ISRW. Okay, current standing wave ratio. Suppose if I write Emax divided by Emin, means electric field max divided by electric field min. Now that is called as the ESWR. The concept is same for each and everything. Okay. So that is called as the SWR is equals to maximum component divided by the minimum component. So what is the maximum value? Already you know maximum value means what? If these two are added, this is called as the maximum value. If these two are subtracted, this is called as the minimum value, right? So that's why 1 plus mod gamma is equal 1 plus mod gamma divided by 1 minus mod gamma. Remaining all will get cancelled. Remaining all will get cancelled. So SWR is equal to 1 plus mod gamma divided by 1 minus mod gamma. So this is a very standard expression. You have to remember this. So SWR is equal to 1 plus mod gamma divided by 1 minus mod gamma. Okay, so in the overlook, okay, by mistake you shouldn't neglect this mod gamma. Always consider this mod gamma. Don't write 1 plus gamma divided by 1 minus 1 minus gamma. Okay, some people will write SWR as 1 plus gamma divided by 1 minus gamma. It is a wrong. Okay, so that's why you have to give importance to this mod gamma. Okay, now what will be the SWR? SWR will be, suppose if mod gamma is equals to 0 means complete matched condition. Now what happens? If it is 0 means complete matched condition. Already you know this. If it is 0 means it is a complete matched condition. Now what will be the SWR? SWR will be 1. So this is called as complete match. Now if gamma is equals to 1 means complete mismatched condition. If you are taking a complete mismatched condition, 1 minus 1, it is infinity. So that's why it is called as complete mismatch. So this is the point you should understand. Suppose if the SWR is equals to 1 means it is the best case. So there is no reflection at all. Okay. If SWR is equals to infinity means it is the worst case. Okay. SWR must be as low as possible. The reflection coefficient must be as low as possible. Okay. The range of the reflection coefficient is 0 and 1 and the range of the SWR is 1 to infinity. Okay. Now from this 1 plus mod gamma divided by 1 minus mod gamma is equals to SWR. Now how can you find SWR? How can you find the mod gamma? Mod gamma is equals to SWR minus 1 divided by SWR plus 1. Okay, it is not simply gamma, it is mod gamma. Okay, so you have to give importance to the mod gamma everywhere. So mod gamma is equals to SWR minus 1 divided by SWR plus 1. Okay. Suppose if you are finding the reflection coefficient from the SWR means just you are finding the magnitude, not the angle. How to find the angle? To find the angle, you have to observe the ZL minus Z0 divided by ZL plus Z0 and from that you should take the angle. If the ZL, Z0 are not given, if the ZL value is exactly not given, now you have to use this. And the positions of voltage maximas minimas are given and from this relation you can get this theta. Okay, from this relation you can get this theta. So you can get the complete reflection coefficient. Already you know the complete reflection coefficient is what? Mod gamma at an angle theta. Okay, so anyhow you should try to find the theta value either by using this or by using this. Right or not? So that is the point you should take care about. Now come to the next one. Suppose if ZL and Z0 are real. Suppose if the ZL and Z0 are real. Now what happens? ZL and Z0 are real and ZL and Z0 are real means it may be open circuit or short circuit. No problem. ZL and Z0. See, observe this. ZL means what? It is a load line, a load. Okay. So if it is open circuit means ZL is infinity. It is a real value. If you take ZL is equals to 0 also, it is a real value again. Okay. You can take any value, any real value. Okay. If ZL and Z0 are real means what? ZL and Z0 means it is a lossless line and a real load. Lossless line and a real load. Now let us suppose if I take ZL is equals to infinity means it is a real load only. Z0 is equals to real means it is a lossless line. Okay. Now if ZL is equals to ZL greater than Z0. So infinity means ZL greater than Z0, right? So if I take ZL greater than Z0 condition, okay, not only infinity, you can take any value. Okay. Suppose if ZL and Z0 are real, okay, and ZL greater than Z0, now what will be the gamma? Gamma will be ZL minus Z0 divided by ZL plus Z0. So you will get a positive value and real value because both are real. Okay, if positive and real means, then what will be the theta value? Theta value will be 0. For a real value, theta is 0. Okay, so this is the point. So that means, suppose if you are taking, see, if theta is 0 means what? At the load, what will be the reflection coefficient? The reflection coefficient is, suppose if I am finding the reflection coefficient at the load, what happens? At the load, what will be the reflection coefficient? ZL minus Z0 divided by ZL plus Z0. So the reflection coefficient is positive and real means the theta is 0. The theta is 0 at the voltage maxima. The theta is 0 at the load. The theta is 0 at the load. Now, suppose if you are taking a complete mismatch condition, now theta is 0 means what? This is called as, this is the condition. Okay, this is the condition. Now, so at here, what is the impedance? The impedance will be maximum. The impedance is maximum means what? What about the voltage? The voltage is also maximum. Okay, suppose if you are taking this one, if theta is 0 means, okay, the voltage at the load, you will get the voltage maxima. Okay. Now similarly, suppose if you are taking ZL and Z0 are real and ZL less than Z0, now what will be the gamma? Gamma will be negative and real. So negative and real means what is the angle of theta? The angle of reflection coefficient. Angle of reflection coefficient is equals to 180 degrees. Okay, you are finding the reflection coefficient at the load. So at the load you will get voltage minima. So because it is observe this, it is 180 degrees. 180 degrees means what? 180 degrees means this case. This case means what is this? It is called as the short circuited load. At the short circuited load, what will exist? The voltage minimum will exist. At the short circuit, what will be the voltage? Voltage is 0. So voltage minima will exist. At the open circuited, what is the voltage? At the open circuited, voltage is maximum. In the short circuit, the voltage is minimum. Okay. So that is the point. So the impedances are coinciding. The impedance maximas are coinciding with the voltage maximas. The impedance minimas are coinciding with the voltage minimas. Okay. So these are the things. So by observing the question, you should identify the answer. Okay. By using this data. Right. Now come to the next one. If ZL and Z0 are real. Okay, I am taking the same condition now. Now you know what is the SWR? SWR is equals to 1 plus mod gamma divided by 1 minus mod gamma. Because that's why I am taking the mod here. Because this is what? Gamma, right? So now if ZL is equals to Z0, if ZL greater than Z0, then this entire value will give you a positive value. This entire value will give you a positive value. And from this, what will be the SWR? So you can take a positive value here, you can take a positive value here. So if it is a positive value, 1 minus positive value, it is 1 plus positive value. Now if you simplify this, you will get SWR is equals to ZL divided by Z0. You will get ZL divided by Z0. So if ZL greater than Z0, now, so you can retain the expression same. So now SWR is equals to ZL divided by Z0. So by observing the values ZL and Z0 are real. So if you want to find the SWR directly, you no need to write first of all reflection coefficient and next 1 plus mod gamma divided by 1 minus mod gamma. This entire thing is not needed. Directly you can write ZL divided by Z0. Right? If ZL is greater than Z0, write ZL in the numerator, Z0 in the denominator. Okay. Suppose if ZL is less than Z0, now what will be this value? This entire value mod of ZL minus Z0 divided by ZL plus Z0 value will be negative. If it is negative, then here you will get a positive value. In the denominator, you will get a positive value. So SWR is equals to Z0 divided by ZL. These are very, very important concepts. Okay. So what are these three? If ZL and Z0 are real, if ZL and Z0 are real and ZL greater than Z0, then the reflection coefficient will be positive and real. Then there exists voltage maxima at the load. Right? If ZL and Z0 are real, if ZL less than Z0, if ZL less than Z0, then what will be the reflection coefficient? The reflection coefficient will be negative and real, and negative and real. Now what happens? Theta will be 180 degrees, means now there exists voltage minima at the load. Right? If ZL and Z0 are real, if ZL and Z0 are real, if ZL greater than Z0, then the SWR will be ZL divided by Z0. ZL divided by Z0. Okay? If ZL and Z0 are real, ZL less than Z0. Okay? For ZL greater than Z0, SWR is equals to ZL by Z0. ZL less than Z0, SWR is equals to Z0 by ZL. Okay? Now, it is clear. Now, come to the impedance matching. If you come to the impedance matching, so why we have to use the impedance matching technique? Okay? So, why we are using the impedance matching? Impedance matching to match the load and the line. So, to reduce the reflections. Okay? So, we will use two types of impedance matchings here. Okay? One is the series quarter wave transformer, means it is a line only. What is a quarter wave transformer? Quarter wave transformer, it is a line of lambda by 4 length. It is a line of lambda by 4 length. Okay? And it is connected in series between the line and the load. Suppose if the line is directly connected to the load, let us suppose we are having some x. Let us suppose we are having reflection coefficient some x. Okay. Now, to reduce that reflection, what we will do that is, in between load and the line, we will put one lambda by 4 line in between. Okay, to reduce the reflection. How it will reduce the reflection means, so suppose if you put the load, the one quarter wave transformer means what? It is a lambda by 4 line. Now, it is having some characteristic impedance. What is the characteristic impedance? The characteristic impedance will be Z0 is equal to the geometric mean of Z0 and ZL. Okay, the characteristic impedance of this Z0 must be equals to the characteristic impedance of this quarter wave transformer. It is represented as Z0 dash is equals to root over Z0 ZL. It is called as the root over Z0 ZL. Right? So this is called as the quarter wave transformer. Now what happens to the reflection coefficient? Reflection coefficient will be ZL minus Z0 dash divided by ZL plus Z0 dash. So instead of writing ZL minus Z0 divided by ZL plus Z0, we are writing Z0 dash here. We know Z0 is less than the Z0 dash because ZL already we know. What is Z0? Z0 is having some value. Now it is multiplied with ZL and we are taking root. So definitely this Z0 dash will be greater than this Z0. Z0 dash will be greater than this Z0. So that's why what happened? ZL minus Z0 dash divided by ZL plus Z0 dash will be having a lesser value, right? So that's why you can reduce the reflection coefficient. Okay, now, so this is one type of matching technique. Okay, this is one type of matching technique, and there are some disadvantages in this matching technique also. Okay, so here as the frequency is increasing and we have to increase as the frequency is increasing and there is a change in the length also, because as the frequency increases, what happens? The lambda will be decreasing. Okay, so if the frequency is varying, according to that you should adjust the length of the quarter wave transformer, and this is one disadvantage. And one more important thing is, so this is only used for the resistive load and lossless lines only. Okay, so that's why. So next we go for the stub matching here. Okay, here we go for the stub matching. So what is this stub matching means? See, here our aim is to reduce the reflection coefficient. Okay, our aim is to reduce the reflection coefficient. Suppose if this is the length of let us suppose this is the long length current transmission line and it is terminated with ZL. Okay, so what is meant by stub means, stub is a short circuited line. It is a short circuited line. Now how the stub matching will reduce the reflection coefficient means, observe this, because it is a mismatched line. So before connecting the stub, it was a mismatched line. So if it is a mismatched line, at different points of the line, okay, you will get different impedances. You will get different impedances. Now what you will do, that is, you have to identify one point which is having a real part of the impedance Z of X is equal to the characteristic impedance. Now what you have to do, and start from here, and you identify one point at which Z of X, already you know Z of X will be having different values at different places. Okay, now you have to identify one point at which the real part of the Z of X will be equal to the real part of the Z of X will be equal to the characteristic impedance of the line. Now identify that point. So let us suppose this is the point. Okay, this point is having impedance is equals to it has the impedance which has a real part Z0. Okay, let us suppose it is having some Z of X. Let us suppose here we are having some Z of X, and this Z of X has Z0 plus or minus Jx. Z0 plus or minus Jx. You can take plus or minus. Okay, what is this Z0? Z0 is the real value of this Zx. Now you have to identify that point on the line. Okay, you have to identify that point on the line for which impedance, okay, the real part is equal to the characteristic impedance. So after observation, now you should bring one short circuit stub and place one short circuit stub there. Okay, now what is the purpose of this short circuit stub? Means it adds inductance or adds capacitance. It adds inductive reactance or adds capacitive reactance. Suppose if you bring one more stub here, and whatever the see, now what I want to do, I want to reduce the reflection coefficient, or I want to try to make the load equals to Z0. Now this entire portion is, for this line, this entire portion acting as a load. This entire portion acting as a load. So that's why I want to make this entire portion's impedance must be Z0. So already you know what is the impedance at this point. The impedance at this point is Z0 plus or minus Jx. Let us suppose Z0 plus or minus Jx. Now what this stub will do? The stub will add impedance, or the stub will add inductive reactance or capacitive reactance. Okay, so this is the Z of, at this point what happens? Z of Z0 plus or minus Jx, this is the original impedance. Now by adding one stub here, what it will do? It will add inductive reactance or capacitive reactance. Okay, suppose if it is a inductive reactance is there, okay, plus Jx is there, and it will add minus Jx. Suppose if it is a capacitive reactance is there in the first term, then it will add inductive reactance, so that these two will get cancelled. Now finally what you will get? You will get Z of Ls is equals to Z0. So ultimately we get the entire load resistance as, the entire load impedance as Z0, because this is the entire line, and for this entire line, and this portion acting as a load, so the load will be now Z0. So perfectly the matching is obtained, right? So perfectly the matching is obtained now. Now at what distance the position must be there? Okay, so from this point to this point is called as the position of the stub. Okay, from load to the point at which the stub is placed is called as the position of the stub. It is called as the position of the stub. It is equals to lambda, Ls is equals to lambda by 2 tan inverse root over ZL by Z0. Okay, now what will be the length of the stub? Length of the line, this short circuit line. The length of the short circuit line is represented with the LT is equals to lambda by 2 pi tan inverse of root over ZL Z0 divided by ZL minus Z0. So by using this length, by identifying the position from here to here, it is represented as Ls, okay, at which the impedance of the line is having a real part equal to the characteristic impedance, and at that place you should place one short circuit stub, and the purpose of the short circuit stub will be whatever the extra term means reactive term is there, and the extra term will be cancelled by using this short circuit stub. Now these are the position and length of this short circuit stub, and these are the expressions. Okay, mostly they are not asking this kind of expressions, but you should remember this, and they are simple also. Okay, and don't write the root to this entire. This is ZL into Z0 divided by ZL minus Z0. The root is only for ZL minus Z0. The root is only for ZL into Z0, not for ZL minus Z0, right? So this is entire the transmission lines. Okay. The next is on waveguides. So why we use waveguides? See, before going to waveguides, so from this the chapter you will be having a 1 to 2 questions every year. So you have to concentrate on this chapter, and they will be very easy for you to solve. Okay. So there are some basic expressions are there you have to remember, and after that you solve some of some 10 to 20 problems on the waveguides. Okay, so easily you can score the marks from the waveguides. See, observe this. So waveguides. So why we use waveguides? So waveguide means generally already we have seen the uniform plane waves, right? Already we have seen the uniform plane waves. So uniform plane waves are, suppose if you take the electric field in the x direction, magnetic field in y direction, and the propagation is in z direction. But in general, the practical waves will not be existing like the uniform plane waves. Okay, generally the practical waves are dispersive in nature. That means the electric field will be traveling in all directions, and it will be directed in all directions, and magnetic field will be traveling in all directions, and the traveling in all directions and directed in all directions. So that means, so generally the dispersive wave will be E of x, y, z, comma t is directed in x, directed in y, directed in z. H is also directed in traveling in x, traveling in y, traveling in z, and directed in x, directed in y, and directed in z. So these are the important things you should understand. So it is generally the practical wave. Okay, so this is the practical wave. So already you know the uniform plane wave, how the uniform plane wave will exist. Okay, how the uniform plane wave will exist. Okay, but it is very different from the uniform plane wave. It is the practical wave. So the practical wave will be traveling in all the directions. Okay, and also the field directions of the practical wave will be in all the directions. Okay, in the previously we have seen E of x of z comma t is traveling in x, h of x of z comma t is traveling in y, but it is traveling in x y z and is a function of time, and it is directed in x y z. So this is a practical wave. But if you observe this, suppose if you want to communicate, suppose if you want to propagate the wave in only the one direction only, now it is not possible to the propagate. So that's why what we have to do, we have to restrict the wave in the unwanted direction, and we have to make the wave to be propagated in the wanted directions. So for that we need some mechanical structures. That mechanical structures are called as this waveguides in general. So what these waveguides will do, that is they restrict the waves in the required directions. That means the waveguides will make the waves to be reflected from the waveguide walls, right? So we'll make the waves to be reflected from the waveguide walls. That means it will confine the wave in only the required directions. In general, the waveguides are the metallic plates. Okay, why metallic plates means? So why metallic plate means the wave has to be reflected from the waveguide wall. Then only it will not go in the unwanted direction. right? So to make the wave to be propagated in the wanted directions, the wave to be reflected from in the wave should not go into the unwanted direction. So that's why we should use some metallic boundaries. Why metallic boundaries means these are the EM waves. So the EM waves will be reflected from the metallic waveguides, metallic plates. So that's why from conductor side, so the EM wave will be reflected from the conductors. The EM wave will be reflected from the conductor, so that we will use the waveguides as the that's why we will use the perfect conducting planes as the waveguide walls, waveguide plates. Okay, so wave means suppose whenever the wave enters into this, so it will not penetrate into the required unwanted direction. Okay, so it will be reflected and it will travel in the final path. Final path means it is our required direction. Let us suppose if I want our wave to be propagated in the z direction, so what these waveguides will restrict the waves in the required direction. Okay, so that's why we have to use the metal plates. Okay, there are two kinds of waveguides here. So one is a rectangular, one is parallel plane waveguide, and one is a rectangular waveguide. So when we use the parallel plane waveguide is, suppose if there exists a wave like this, if the electric field is traveling in x and z, if the magnetic field means if the EM wave is traveling in x and z, so it is not traveling in y. That is the point. Suppose if you find the wave like this, then we should go for the parallel plane waveguide. Y means I want the propagation only in z direction, so that I have to restrict the wave in x direction, right? So that's why I should only restrict in one side, means only in x side. So for that I need one dimensional restriction. If it is one dimensional restriction means in x direction the wave is restrict, only the wave is propagated into the z direction. So for that purpose we use the rectangular waveguide. So it is the rectangular waveguide. This is one plate, this is one plate. Now the one plate is placed at x is equals to 0 and one place is placed at x is equals to a. This is called as the guide separation. Now for this waveguide, now if you place one time harmonic source here, this time harmonic source will generate an EM wave, and that EM wave will be transmitted into this waveguide, and it will be reflected and it will transmitted into the final path. Okay, it is transmitted into the final path by multiple reflections. Okay, so it is traveling in a zigzag path. So now here the propagation constant is defined as, see, we use the boundary conditions of the electric fields, and from that we will define the propagation constant along the guide axis. Gamma bar is equals to root over m pi by a whole square minus omega square mu epsilon. Okay, omega square mu epsilon. Here mu epsilon representing the material we place between the two conducting plates. So this is called as the propagation constant. Okay, along the guide axis. It is along the guide axis. Okay. So now suppose in this propagation constant, so always we should remember, even it may be in the EM waves, or it may be in the transmission lines, it may be in the waveguides, always the propagation constant must be purely imaginary. Okay, suppose if you observe this, if m pi by a whole square minus omega square mu epsilon is greater than, see, if this is the relation is maintaining, now what happens? Then gamma bar is equals to real, because this value is more when compared to this, so that's why gamma bar is a real. So real means what? Gamma bar real means only the attenuation takes place, there is no propagation. So this is the very, very important point. So there is no propagation at all. So we should not follow this condition. Okay, so the wave to be propagated into the medium, this must be less than this value, so that in under root you will get a negative value. Okay, if it is under root you are getting a negative value, means it is like a purely imaginary value. So mod gamma is equals to 0 plus j beta bar. So this is, see, gamma bar is equals to 0 plus j beta bar. That means the propagation constant along the guide axis, along this path, the propagation constant along this path will be purely imaginary, means there exists a propagation. Okay, there exists a propagation. So this is the minimum requirement. So now, if you deduce this equation, then you will get omega c, cutoff frequency. It is the boundary, okay, below which there is no propagation. Okay, omega c is equals to m pi c divided by a, fc is equals to mc by 2a. Right? So if you reduce this equation, we will get a cutoff frequency m pi c divided by a. C means it is the light velocity or the phase velocity. Okay, if it is the light velocity in the free space. Okay, suppose if this waveguide is filled with any material, now c divided by root epsilon r. So that is the point you should understand. Okay, so this is fc is equals to mc by 2a. M nothing but it's in the sign solutions. Okay, so m is equals to 0, 1, 2, 3, 4 like that. Okay, so from this lambda c is equals to 2a by m. So it is called as the cutoff wavelength, cutoff frequency, cutoff frequency. It is the cutoff frequency in the hertz, in the cutoff, it is the cutoff frequency in radians per second. Okay, so now, so what is the minimum propagation frequency? What is the minimum frequency to exist the propagation? So you must maintain omega c must be greater than fc. So you must. So if you deduce this equation, you will get this condition, fc greater than mc by 2a. If you deduce this equation, okay, so you will get f, the frequency, the minimum frequency must be greater than fc. So it is called as the fc. So below which there is no propagation. Fc is the cutoff frequency. Below the cutoff frequency there is no propagation. So the wave to be propagated into the medium, you must maintain the frequency greater than the cutoff frequency. So this is the very important point. So the wave to be propagated in the waveguide, the cutoff frequency, the frequency must be greater than the cutoff frequency. Then only the wave will be propagated. Okay, what happens if exactly f is equals to fc? If f is equals to fc means what? This one is equals to this one. So the gamma bar will be 0. There is no propagation at cutoff frequency also. At this gamma bar is equals to 0. Okay, the wave resonates between the guide walls. It resonates between the walls. Wave resonates between the guide walls, but there is no propagation. What happens if you give fc is equals to fc? The wave is not going like this. It will be resonating between the guide walls. It is not propagating in this direction. This is the point. Now what will be the phase velocity? So after the wave is entered into the waveguide, now the phase velocity along the guide axis is represented as Vp bar is equals to omega by beta bar. This will be equals to root over 1 minus fc divided by f whole square. And this can be equal to c divided by cos theta. What is theta means? It is the angle made by the wave with respect to the guide axis. This is called as the wave angle. Where from this, if you compare this, then theta you will get sin inverse of fc by f. So this is called as the wave angle. Okay, suppose if fc is equals to f, observe this. If fc is equals to f means exactly at the cutoff frequency, what happens? If fc is equals to f exactly at the cutoff frequency, what happens? Theta is equals to 90 degrees. How the wave will be? The theta will be how much? 90 degrees. That means the wave is projected like this. So that's why the wave will be resonating at this place only. It is not moving forward. Suppose if f is greater than, if this denominator is greater than the numerator, now the theta will be less than 90. If theta is less than 90 means it will be inclined like this. If it is inclined means definitely it will be reflected, and definitely it will be reflected. So that's why the wave will be traveling in the required directions. So this theta is called as the wave angle. Okay, similarly what we are getting, suppose if you observe this relation, you will get Vp is greater than c. See, whenever Vp is equals to c divided by cos theta, what is the maximum value of theta? The maximum value of cos theta is 1, right? The maximum value of cos theta is 1. So that's why if you Vp is equals to c divided by less than 1 value, so that's why maximum value of 1 means, maximum value of cos theta is 1 means, so in between 0 and 1, so it is producing a velocity okay, greater than the light velocity. So this value will be is greater than the light velocity. See, observe this. It is C. It is the light velocity divided by cos theta. Okay. Suppose if theta is equals to 0, what happens? VP is equals to C. Suppose if theta is equals to 90 degrees. If theta is equals to 90 degrees means it is 0. Cos theta is 0. VP is maximum. So the minimum value of VP is how much? C only. The maximum value is infinity. Okay. The VP is maximum. So the minimum value is C. Maximum is, there is no limit for this. Okay. So VP greater than C. So this is called as the phase velocity. In general, the phase velocity will be greater than the light velocity, greater than the greater than the velocity of the wave in the free space. Okay. This is a very important point you should understand. The phase velocity of the wave in the waveguide greater than the wave in the free space. Okay, greater than that of the wave in the free space. Now from this, so what is the meaning of this one is, why it is happening like this means, so if you reduce this equation, you will get lambda bar is equals to lambda divided by cos theta. So it is because of the wavelength appears to be the wavelength. Observe this. From this one also what we can write? Lambda bar is equals to lambda divided by cos theta. So from this one also what we can write? So lambda bar is greater than lambda. Lambda bar is greater than the lambda. Let us suppose lambda bar is the wavelength along the guide axis, lambda is the wavelength in the free space. Okay. So because the lambda bar is greater than the wavelength in the free space, now so that's why the phase velocity is greater than the velocity of the wave in the free space. Okay. So that's why it is happening like this. Okay. Because the velocity and the wavelengths are in proportional relation, right? So if you reduce this equation, you will get lambda g square. Lambda g square. See, observe this. This is lambda bar, right? It can also be represented as lambda g. What is lambda g? Lambda g means the wavelength along the guide axis. This is also called as the guided wavelength. This is also called as the guided wavelength. It is also called as guided wavelength. So this is the relation between the guided wavelength and the cutoff wavelength and the wavelength in the free space. See, what is this lambda? Lambda means wavelength in the free space. What is C? It is the velocity in the free space. What is VP? It is the velocity along the guide axis. VP bar is velocity along the guide axis. Okay. What is lambda bar? Wavelength along the guide axis, also called as guided wavelength. So 1 by lambda g square is equals to 1 divided by lambda square minus 1 divided by lambda c square. So this is one important relation. Okay. And if you know the cutoff frequency and the operating frequency, it is very easy to calculate the guided wavelength. Okay. So this is the phase velocity. Now there is a group velocity. See, already you know the phase velocity is defined as omega divided by beta bar, right? The phase velocity is defined as the omega divided by beta bar. But the dispersive waves, okay, the dispersive wave will be having different frequencies, okay, different frequencies in different directions. So that's why what we will do, so we cannot expect the linear phase in the waveguide. Okay, so that's why the group velocity is defined here. The group velocity Vz is equals to d omega divided by d beta bar. Already we will be finding the beta bar there. Okay, by this you will find the beta bar. Okay, for that beta bar you have to divide the beta bar with respect to omega. Okay, if you invert that, d omega by d beta you will get. Okay, so Vc is equals to c into cos theta. Here c into root over fc divided by f whole square. So it is like what? It is fc is equals to, so observe this, if theta is equals to 0, if theta is equals to 0 means what? Theta is equals to 0 means fc is 0. Okay, theta is 0. Yes, if theta is equals to 0, what happens? If theta is equals to 0, now this will be the Vc is equals to C. If theta is equals to 90 degrees, then the Vc is equals to 0. Okay, what will be the maximum value? The maximum value of the Vc is C only. The minimum value is 0. So that's why Vg less than C. Okay, the group velocity always less than the C. Okay, from this relation and this relation, from this relation and this relation, if you multiply these two, C is equal to root over Vp into Vg. So the light velocity, the velocity of the wave in free space is equal to the geometric mean of the phase velocity and the group velocity. Okay, so these are the basics now. Okay, now in this waveguide, in this parallel plane waveguide, okay, suppose if I want to define the TE wave. So what is meant by TE wave means, the TE wave means already you know, E must be perpendicular to the final path, propagation. Okay, E must be perpendicular to the propagation. So this is the point you should understand. The transverse electric wave. Transverse electric wave means the electric field must be transverse to the propagation. That is the point. Okay, so that's why there must not be any. What is the final path? The final path is what? Z direction, right? So that's why there must not be any electric field component in the Z direction. So that's why then only this is possible. The electric field will be perpendicular to the propagation. If this is 0 and finally you will get these three components. Okay, suppose if you observe the TE wave solutions and TM wave solutions, you go to the TE wave solutions and the TM wave solutions, okay, and there you will get these three expressions. Okay, the electric field in the direction of Y. Okay, so how the electric field, observe this, how the electric field will be in the direction of Y. It is Z, right? It is X. What will be Y? This is Y. If the wave is propagating like this, the electric field will be always perpendicular to the final path. Okay, so this is called as the transverse electric wave. So remaining H will be existing in X and Z. Actually, this is the path. What is this actual path? This is the actual path. This is the final path. Okay, actually the wave is traveling like this, but this is our final path. Okay, this actual path is X and Z. Okay, here because this is a transverse electric wave, this electric field, only the electric field is transverse to the propagation, and there is no restriction on the magnetic field, and it will be propagating. They will be the field will be, observe this, the magnetic field will be in the direction of propagation. In the direction of propagation. What is the propagation? The propagation is X and Z, actual propagation, right? So this is the TE wave. Now what about the TM wave? So TM wave means here the magnetic field, the transverse magnetic wave, right? So the magnetic field must be transverse in nature. So that means here the H must be perpendicular to the final path. The H must be perpendicular to the final path. Final path means what? Propagation, right? Final path means propagation. So that's why there must not be any magnetic field component in the direction of Z. So that's why Hz is equal to 0. Okay, if Hz is equal to 0, some components will become 0. Suppose if you are observing, some equations will be there. Okay, so if you go there and if you observe that equations, then you will get H of X comma Z comma T of Y. That means only you will get the magnetic field component in the Y direction. Okay, now there is no restriction on the electric field. Here the wave is transverse magnetic wave. Because it is a transverse magnetic wave, the magnetic field is transverse to the final path. So only the magnetic field will be in the Y direction. Now the magnetic field is in this direction. Okay, it is the final path. So this is this direction is perpendicular to the final path. Okay, so that's why this is called as the TM wave. Okay, now one more mode will be existing here. Suppose if I put Fc is equals to 0, let us suppose Fc is equals to 0. Okay, let us suppose if any waveguide is defined. Okay, if Fc is equals to 0, Fc is equals to 0 means, observe this, the cutoff frequency will be 0, right? So when the cutoff frequency will be 0, if M is equals to 0, if M is equals to 0 means this is called as, if M is equals to 0 in the TM wave, you will be having TM wave solutions and this one will be having a TM wave equations. Okay, so in that equation, if m is equals to 0 in TM wave, if I put m is equals to 0, then you will get a TEM wave. Okay, so how the TEM wave? Transverse electromagnetic wave. That means transverse electromagnetic wave means the electric field is transverse to the propagation and magnetic field is also transverse to the propagation. So this is called as the transverse electromagnetic wave. Okay, so in the TM wave solutions, if you put m is equals to 0, that will become a TEM wave. Okay, suppose if I put m is equals to 0 here, then now what will be the cutoff frequency? Cutoff frequency is 0. Now what will be the theta? Theta is equals to 0 because theta is equals to sin inverse Fc by F. So theta will be also equals to 0. So what is theta is equals to 0 means? So it is theta. So theta is 0. So theta 0 means this is called as the TEM wave, transverse electromagnetic wave. Okay. So there is no zigzag path there. It is a perfect uniform plane wave. Okay. Now, so here the mode. What is meant by mode means it is a physical connection of the input. It is a physical connection of the input is called as the mode. Okay. So here m stands for the mode. Okay. If m is equals to 1, the first, it is called as the first mode. Okay. If m is equals to 1, it is called as the first mode, and for each and every mode the cutoff frequency is defined. Okay. Fc1 is equals to C divided by 2a. Okay. If this is for the first mode. Okay. If m is equals to 2, Fc2 is equals to C by a. Okay. If m is equals to 2, Fc2 is equals to C by a. So what is the meaning of operating in the first mode means? Let us suppose if m is equals to 0, m is equals to 0 means the cutoff frequency, the operating frequency must be in between 0 and infinity, right? So which kind of wave will be having cutoff frequency 0? Only the TEM wave will be having a cutoff frequency 0 means if the waveguide is operated in the TEM mode, then it will allow the DC also. It will allow the DC waves also. Okay. So that is the point you have to understand. Okay, the waveguide to operate, the wave to be propagated into the waveguide, the minimum frequency must be greater than the cutoff frequency. Okay, suppose if m is equals to 0 means that is called as the TEM mode. So it will allow all the frequencies from 0 to infinity. Suppose if the wave is operated in the first mode, then the frequency must be maintained in between Fc1 to infinity. Okay, if it is operated into the second mode, Fc2, the frequency must be in between Fc2 to infinity. So that is the point. Okay, suppose if the waveguide is operated into the second mode, that means this frequency is greater than Fc2 and as well as Fc1. Okay, so from this what we can say? Definitely it will be what? Fc2 is less than Fc2, this value will be greater than this value. Okay, the second mode cutoff frequency will be definitely greater than the first mode cutoff frequency. Suppose if any wave is operated into the second mode means by default it is operated into the first mode also. So from this what we can say, if any waveguide is operated in the higher order modes, then by default we can say that they are operating in the lower order modes also. Okay, suppose if any waveguide is operating in the 10th mode, okay, now we can say that waveguide is connected in the 9th mode, 8th mode, 7th mode, 6th mode, 5th mode, 4th mode, 3rd mode, 2nd mode and 1st mode. Okay, so like that. Okay, now what will be the intrinsic impedance of the waveguide if it is operated into the TE mode and if it is operated into the TM mode? So the intrinsic impedance of the TE mode will be 120 divided by cos theta. For the TM mode 120 pi divided by cos theta here. Okay, for the TM mode the intrinsic impedance will be 120 pi into cos theta. Okay, so the TEM mode, for the TEM mode what is the cos theta? Cos theta will be how much? If theta is 0, right, for the TEM mode, so cos theta will be 1. Okay, so that's why for the TEM mode 120 pi, either you can write this formula or this formula. Okay, you will get 120 pi only. Okay, now if you come to the rectangular waveguides, okay, in the rectangular waveguides, what you can observe? In the rectangular waveguides, there are, see, when you will use the rectangular waveguide, if the waves are like this, if the wave is traveling in x, y, z, 3 directions, and it is directed x, y, z. So if this is the case, it is a perfectly dispersive wave. Okay, if exact dispersive wave is there, now we use the rectangular waveguide, because we don't want the propagation in x and y direction, we want the propagation only in the z direction. So I want to restrict the wave in x and y z direction, x and y directions. So that's why I have to put 2 plates in x direction and y direction also. In x direction and y direction also. It is a rectangular pipe. Generally, what is this waveguide? It is a rectangular pipe. Okay. So here I have to use the boundary to x is equals to 0 and x is equals to a, y is equals to 0, y is equals to b. Similarly, as we defined the propagation constant along the guide axis, here also we will define 2 sine functions are there and 2 sine solutions will be there. As we are getting m pi by a whole square, here one more term we will get n pi by b whole square minus omega square mu epsilon, and from this we will define the cutoff frequency, this one, and cutoff frequency is equals to, either you can represent it in omega or we can represent in FC. FC is equals to c divided by root over m by a whole square plus n by b whole square. Okay. Now sin theta and Vc and Tm, Te, these all are similar to the parallel plane waveguides. Okay, as in the rectangular waveguides. But very one more important point you have to understand, that is, here Tm mode exists, Te mode will exist, but Tem mode will not be existing in the rectangular waveguide. Okay. So the rectangular waveguide will be existing only 2 distinct conducting planes between the 2 conducting planes. But if you observe that it is a single conductor. It is single conductor shaped in rectangular form. Okay. So in this kind of rectangular waveguides, now there is no TEM wave will be existing. Okay. And one more important thing is, suppose if you put m is equals to non-zero, m will be there and n is equals to 0, or if you put m is equals to 0 n, then TEM0 and TE0n will exist. Okay, TEM0 and TE0n will exist. Okay, you will get the equations from the TE and TM wave solutions will be there, and go to there and read that. Okay, suppose if you put m is equals to 0 or n is equals to 0, perfectly there exists TE0m, 0n and TEM0. Okay, suppose in the TM wave solutions, if you put any of these 2, either m0 or n0, those waves will not be existing. So m and n must be a non-zero values. Okay, and these 2 are called as the evanescent modes, and TE10 and TE01, these 2 are called as the dominant modes. And it is dominant mode. What is the dominant mode? The mode which has least cutoff frequency is called as the dominant mode. The mode which is having a low cutoff frequency, that is called as the dominant mode. Right? Suppose TE10 mode, now what will be the cutoff frequency? The cutoff frequency will be in this MC by 2A. Right? MC by 2A. Suppose if n is equals to 0, what you will get here? If you put n is equals to 0, then Fc is equals to MC by 2A. Suppose if I put m is equals to 1 here, then Fc is equals to C by 2A. Right? Here for this, what is the cutoff frequency? C by 2B. Okay, suppose C by 2A and C by 2B. In C by 2A and C by 2B, suppose A greater than B, now what happens? The cutoff frequency of this one will be less than the cutoff frequency of this one. Okay, so if A greater than B, you will get a TE10 mode as the dominant mode. Okay, and suppose if A less than B, now you will get the TE01 mode as the dominant mode. So these are all required, and go to the waveguide concept, and these are the important expressions. Okay, the thing you should remember, that is, you should concentrate on these T and TM wave solutions for the rectangular waveguides and the parallel plane waveguides. Okay, so this is all what about the waveguides, and this is enough, and you solve some important questions, and definitely it will be useful. Okay, these sin theta and intrinsic impedance, these are all important. Okay, now come to the antennas portion. So here you should remember the basic terms and definitions. What is a gain, what is a power gain, what is a directivity, what is a directive gain, what is the radiation resistance, what is the radiation efficiency. Okay, these are all required, and before that, and also you should remember what is the angle, plane angle, what is the solid angle, what is the beam solid angle. These all things you should remember. Okay, all formulas must be remembered. What is the effective length, what is the effective area. Okay, these are all required. Okay, and also what is the, if you come to the antenna arrays, mainly there are two kinds of arrays are there. N is equals to, see, observe this, broadside array and end fire array. Okay, so for broadside array and end fire array, this is the total phase. The total phase factor is equals to alpha plus beta d cos theta. So based on this, you will be getting the questions. In the 2009s, we didn't get any question on this arrays, but we got the question on the radiation resistance. The radiation resistance is equals to 80 pi square dl divided by lambda whole square. It is for the Hertzian dipole. So generally this is Hertzian dipole is in the length between lambda by 15 to lambda by 25. Okay, it is very small length. Okay, it is very small length. Okay, so this is called as the radiation resistance. Okay, and it is for electrically short dipoles, it is the radiation resistance. Okay, and it is electrically short monopoles, it is pi 10 into pi square L divided by lambda whole square. Okay, suppose if you take the half wave dipole, this is the 73 ohms. Suppose if you take the quarter wave monopole, means lambda by 4 length antenna. So this will be this is by half. Okay, 73 divided by 2. Okay, suppose if you take L is equals to lambda by 6 line. If you take a lambda by 6 line length antenna, suppose if the length of the antenna is lambda by 6, now what will be the radiation resistance, means RR divided by 3. Okay, so this is for lambda by 2. So this is by lambda by 4, means you have to divide it by 2. Okay, this is for lambda by 2. Now if I want the radiation resistance for lambda by 6, means I have to divide with 3. Suppose if you take the lambda by 8 length antenna, then the radiation resistance will be RR by 4. So mostly you should, when you come to the antennas, you no need to focus, no need to struggle with the antennas. Just a simple, observe this, simply what you should do, you should go to the basics, terms and definitions will be there. Okay, and after that, what are the terms of gain? Already you know gain, radiation power density, radiation power intensity, and some terms will be there. What is the directivity, what is the effective length, what is the effective height. Okay, and after that, and you should go for the antenna arrays for 2 element array and for n element array, and there you get the error factor. Okay, normalized error factor, and you find the normalized error factor. Okay, mostly these are the 3 to 4 concepts are there, you should remember. Radiation resistance for each and every length is must, and also basic terms and definition, and also the antenna arrays. In antenna arrays there are n is equals to 2 elements, n is equals to 2 elements are there, and n is equals to n elements. Okay, n elements. Now radar range equations. Okay, radar range equation, and go to the range equation. Okay, and observe. So what is a radar and what is a range equation, and what happens to the range? Suppose if you want to double the range, what we have to do? The transmitted power, what must be the sensitivity? Okay, so what must be the diameter, means effective length, or sorry, effective height, not effective height, effective area. What happens to the effective area? Okay, there are some parameters will be influenced. Suppose if you want to double the range, or if you want to change the range of the radar. Okay, so these are the things. So this is overall EMT. Okay, I hope you got it. Okay, thank you very much, and definitely it will help you, and make use of this. Okay, so whatever I told for antenna, that is enough. Okay, so you go to there and with patience you have to work for one day on the antennas, radars. One day antennas or radars, you will get minimum 1 mark. So no question will be left in the examination, right? No question will be left in the examinations. Okay, thank you, all the best. So please comment if there is any requirement, please comment. So just now we are busy with our shooting, so that's why. So we don't find time, and so even though we worked on it, okay, to help you, and thank you very much, and all the best for your examination. Okay.